Okay, good morning. This is Deep Generative Model. So we have 3 weeks left, including this week. We have already covered a lot of topics like transformers, GPT, and recently in last 2 weeks we covered diffusion models, denoising diffusion models, and including the architecture of stable diffusion. So in the rest of the 3 weeks, we are going to cover more advanced techniques and topics. Although the topics we're covering, like the transformer or uh, reinforced in, uh, reinforced learning with human loop feedback, and like the diffusion models, they are all new topics. But because they are so popular and very trendy, very hot research areas, so there are a lot of new development in these areas. And just like what we are going to discuss a little bit later, in the area of diffusion models, there are a lot of different approaches that looks very promising. So we're going to cover a few approaches that I think that is very promising and may become more and more popular in near future. And also, we'll have our last homework next week. So that will be our last homework. Okay, so let's start with today's topic. Today we are going to talk about some more advanced development in the area of diffusion models. We are centering around the stable diffusion 3. But since stable diffusion 3 is architecture and a model that including a lot of useful materials and useful techniques and useful researches in the current development. It uses everything it can, every knowledge we have for diffusion model to improve these new models with all possible cost. So effectively, we were talking about a lot of practical result about the diffusion models, a lot of new useful techniques that can be used in diffusion models. And also, when we talk about diffusion models, we are covering also a new approach that called flow matching or rectified flow. They are very literally they are technically they are different with diffusion models in some sense, but they are very similar. So I will give a umbrella 10 of diffusion model to cover all of them altogether. So after all, this model is still called the stable diffusion. There's also a diffusion in it. So we're going to just include them as one of the approach of the diffusion models. Okay, so because we are going to cover a lot of new techniques, so at the very beginning, you will see that I'm going to talk about uh, different papers, not the papers of the stable diffusion. I'm going to talk about like 4 or 5 different papers that has totally different name and developed by different researcher groups. But we'll get there. We're going back to the stability. All of this stuff are related to the stable diffusion 3. Okay, so for the first technique that we are going to cover is the a paper called EMU, enhance EMU, enhancing image generation models using photogenic needles in haystack. This one is developed by Meta, so total different company. So what is this paper about? Let's see the result first. So these are the results generated by the EMU. What do you think about this image compared to the image generated by like Stable Diffusion 1.5 or 2 or like Imagine by Google or Midjourney? One of the feature characteristics of this picture is they are more visual appealing. They have more aesthetic properties in these features, in these images. They look good, like a photo taken by a professional photographer. Their contrast, their color tune are more like a more on purpose. Not some random guy use a random smartphone, take a Photoshop like a group photo or random photo in some place. It seems to be more artistic, more visual appealing. So that's the purpose of this paper. It is trying to develop a method to improve the aesthetics of the image generated by the diffusion models or the image generation models in general. There are many different aspects of how we evaluate a model, image generation model. So like speed, like the image quality. So even for image quality, there are different aspects to feel the image quality, like the fidelity, the variety. And this is one specifically for the visual appealing. So the main contribution for this paper is it outperformed SDXL. SDXL is one of the milestone, or I think cell diffusion 1.5 is one of the milestone, and also cell diffusion 2.1 or 2.0, but are also very important, but not as important as Stable Diffusion 1.5. Stable Diffusion XL is more like comparing target to other research results. So outperforms SDXL is something, and you can see that EMU outperform SDXL, but not so fast. It's only in one aspect, the visual appeal. So how did this EMU do? What does EMU do to get it outperform, to beat the SDXL, at least in visual appeal? So one thing it does is to provide a recipe for good fine tuning, so that the image can be more aesthetic alignment to text to image model for image models. So and this recipe works for other diffusion based architectures. Sorry. In this recipe, we are going to cover this recipe, but the the part that Stable Diffusion used in for the major part that Stable Diffusion 3 used is only for the latent diffusion models. So although this recipe, there are many different parts of this recipe, and many of them works well for diffusion model or other image generation models. But the part we are going to use in Stable Diffusion 3 is only for latent diffusion model because it is uh, about the channels of the how many channels we should have in the autoencoder. So this is a major result that we can use. Recall that in Stable Diffusion 2 or Stable Diffusion 1, the autoencoder has only the latent space only has 4 channels. So suppose we have image of 256 by 256 and 3 channel of color, 3 color channels RGB. Then the latent space is going to be 32 by 32, and it has only 4 channels. In the study of emu, we sorry, I'm having a cold, so I have really uncomfortable. So I'm going to get cough often. So when I stop or pause, that is because I don't feel good about my throat, so I have to cool down it a little bit to wait it to stop to getting better. Okay, so these are models. AE stands for autoencoder. So how does the email train its autoencoder? So by the way, it also works in using a latent diffusion models architecture. So how does this autoencoder works? So the study shows that the experiment shows that when we use more channels, the performance getting better. So one of the key is to increase the channels of the encoder. And also, this paper states that when training the autoencoder, it also uses the adversarial loss, just like the PQ game. And it doesn't feed the model with the RGB channel as input directly. It uses a Fourier feature transform to transform the channels into a more channel as an input. So the Fourier feature transform or Fourier feature models is one of the I think it is significant popular approach. At least it's one technique that you should consider when you wish to control to build your model architecture. So this is one of the things that you can consider. It is can capture high frequency properties or characteristics in the images. So that's one of the benefit. And this paper is also, I think, is 2020 or 2022 or 2020, maybe 2020. One of the spotlight paper in, if I remember correctly, is CVPR. So it definitely worth reading. In this paper, in email paper, it doesn't describe clearly how does it apply the Fourier feature, but uh, I'm guessing it's using the standard Fourier feature. So the basic result is that more channel is better. And when email training the autoencoder, it also uses the adversarial laws and also with the Fourier feature as the input. That's the flavor of the training of the autoencoder that the email use. Along with this, it also comes with some techniques like the automatic filtering, and the second stage use the human filtering. And in human filtering, it also has two stages. So let me describe the workflow, the process of the data preprocessing. We'll talk about a lot of different techniques about the used in Stable Diffusion 3. We'll start from the easy one first, and later we'll come to some more difficult or more abstract ones like the flow matching, and also we'll cover the architecture of the DIT, the diffusion transformer. But we'll start with some more easy ones. The easy ones are used for data processing. Although the email data processing is not exactly like the same as the Stable Diffusion 3, but one key important feature is uh, that you should do some filtering or to get a more clean data to do to train your model, because garbage in, garbage out, and in the realm of image generation, it is very crucial that you have high quality data. This affects a lot of the image quality that generated by your model. So if you have, you think you need to improve your model. So one thing you should consider is to clean up and increase the quality of the data set. Although it is in general more data, the better, but the image quality is also a key point. One thing is that because we only have that much time, so if we already have enough data, lot of billions of data, image data, we probably have already enough data relative to the time we have or computational power we have. So maybe considering cleaning up your data is a good idea. However, in general, when we're training a diffusion model like this one, a general diffusion model, a general text to image model, I say, so not only diffusion model, we wish to train a general text to image model, we usually need a lot of data. How much data it is? Like several billion of images. It's very typical. Or at least we have like several million of images. A popular data set is Lion. Lion has two variations. One is 400 million. So it has 400 million of image and text pair. But the full data set is like 5 billion. Another popular dataset for training text to image generator is CC. CC has two variations. One is CC 3 million, and the other is CC 12 million. They are using to train also like the text image caption, but it is also very frequently using them to do the text to image to train the text to image models. Because there are also some other image model, image dataset that contains billions of, like I remember it's like crowd image dataset, like three, it has 3 billion or something like that. So typically we have billions. It is not unusual that we train our models with billions of image, or at least several millions images, text image pairs. But you can imagine that it is very difficult to construct to build such dataset. How do you even start with and to construct this dataset, like billions of text to image pairs? It costs a lot. And all dataset I mentioned is publicly available. Although you only can download them, the a list of the image URL, and you have to run through the list and download the image from the internet by yourself. So it's typical you can only download like 70% of the images, because maybe like 30% or 20% images are permanently removed from the internet, so you can no longer reach them. But we can imagine that we collect billions or billions of image from internet. That's something we can imagine, because that is essentially what the search engine do, like Google or other search engine do. We just crawl the internet and collect the URL of images. The difficult thing is to generate the text according to the images. Billions of these pairs requires a lot of people to do annotation if you wish to do it with human beings. So it usually come with some automatic process. So people generate the captions using automatic process. So in the past, because we are getting the images from a web page, so we can maybe, so in the HTML, in a web page, an image usually has a alternative text or description of the image. So maybe we can use that. So sometimes we can use that, and sometimes we can use the text around the images, nearby the images, to as a description of the images. So that's one of the way to do that. The other way is using a image caption. You train an image caption model so that you can generate the caption by the image of the image. Like using, we're calling it a little bit later. But at the very beginning, this model, this image and text pairs are used to are collected because we want to train an image caption model. So we don't really have a good image caption model. So at the early years, we have to have some workaround to use other ways to generate the corresponding text for the image. And the other way is to hire people, real human, to do the annotation. So it is doable because if you really think about it, if you have 1,000 people, each one annotating annotates 1,000 images, then you have 1 million images. So if we are using some kind of crowdsourcing, it is reachable. However, it is still difficult to control the qualities of the annotation. So that will be an issue. And another issue is the image quality itself. It is difficult to have an image that has a good quality. So like I said, the Lion is one of the popular dataset that has a lot of image and the text pair in it. But it does have a lot of images. So a lot of images have low qualities, doesn't have a good qualities. So there are actually a lot of different subset of the Lion dataset. So one of them is to choosing the images that has higher resolutions, and some of them are using it to choose images that with human face in it, and some of the subset is to choose an image that is has a better aesthetic feature or more visual appealing, more beautiful, more pretty images, more artistic images. Okay, so for an email, well, I mean we can do that automatically. So email do it in the first stage because we have billions of images, many billions of images, maybe come from different data source. So we start from automatic filtering because there are too many images. For an email, it doesn't care about the text quality. It only cares about the image qualities. So like we said, the dataset may contains crappy images, may contains low qualities text. So both image and text may contain some quality issues. The email focusing on the image quality because we have a lot of millions of billions of images, so we start from filtering them automatically. So we can filter out something really obvious, like it has padding or really low resolutions or very strange aspect ratios, and we can actually train a model that do to judge the image quality for us. This is a very popular way to do that. So when I train some models using a dataset, maybe collect by the third party or collect by the customers, the first thing you should ask is this dataset has a good quality? Does this dataset has errors or wrong annotations in it? So we usually do a automatic search to search something obvious. Very often you will find that you can find a lot of wrong annotations or questionable annotations, even with some very simple algorithm. Okay, so this one is same. We usually do it automatic filtering first. So the images can be reduced to a few hundred millions. Then it uses human to filtering. The human also has two stages. So the first one is the more general people. That means the non-expert So using some, you can translate it as cheap labor to down select the image pool to 20,000 images. Then the second phase is to ask the specialist expert to do the further selection. So you can see the logic is pretty clear. We use a cheap method to do the early stage to reduce the number of image to a small number. And when the number become smaller, we can use a more expensive method to do the more detail and more fine tuning, more fine filtering. So at the last stage, we can use actually the expert to do so. So at the last stage, we only have 20,000 images. So the expert can judge the image by the composition. So this is the composition is how the objects, the position or the size are in the image, like the rule of 1/3. Those kind of photographic rules for taking photographic rules. So the expert can use these rules to judge, okay, this one is a good picture or this one is not. And the lightning, does this photography has a good enough lighting, and the color and the contrast. Does I think this paper they are asking the expert to choose the images with more colorful images. So there are many different standards of how is the good color and contrast. But they are choosing more colorful images and choosing the subjects and background. And it also includes some subjective assessment of does this photo express some emotion or something like that. Okay, so we have a few criteria that is more difficult to or require more experience. Then we can ask the specialist annotators to do the to filtering the further image. So after this filtering, they use this rather relatively small dataset to fine tune the origin model. Then it get the better performance, more visual appealing. So here you can see some results to get an idea of the goal they wish to achieve. So I think they are doing a really good job because at least the image they demonstrate has a really good quality in the aesthetic. Okay, and another paper here is titled with the imagine. Oh, okay. This one is not. This one is the follow-up paper. This one is a follow-up paper of the of the email. This one I think is just published last month in April. It is a follow-up work of email to make it run faster, but remain the same quality. The next paper we are going to talk about is the DALL-E 3 paper. DALL-E is probably the first text-to-image model that achieve modern the good qualities or some qualities that acceptable by human beings. At least I think DALI 2 did it. So this one is a paper for DALI 3, the latest generation of the image generative models provided by OpenAI. The DALI 3 paper is not that exciting because it doesn't provide new architecture, new insight, or new things. Instead, it only focuses on one thing: to clean up the dataset, just like what the email does. But it is focusing on the text part. The email is focusing on the image quality part. And it is only do the fine tuning because we can only have that much good quality images. We are unable to generate more good quality images. If we can do so, we already achieve our goal. There's nothing left to do. So we can only filtering the dataset to get a small dataset, a smaller dataset that has better quality images. But for the text, it's a different story. Because we can in fact, if the text is not good, we can in fact generate a better text corresponding to the image that we have. So DALI 3 is focusing on this part. So that is probably why they didn't put this paper in the spotlight. Because if you go to the DALI 3 webpage, you can see that usually they put the research paper on very top of the website. So you can very quick link to the paper or technical report about the model. But the DALI 3 paper, it is somewhere in the middle of the web page. So you can still find it, but I don't think it is put it into the focus. Probably because it only focusing on how to clean up the data. So it may not seem to be that appreciated. But I still think this one is very useful advice. And the result, the experience result is very, you can get a lot of information or insight from it. So the basic idea is that the prompt found ability is affected by the text prompt, the text in the dataset. So if you don't have a very accurate or detailed description, have a very low quality text in the dataset, you cannot train a very good image data, image generation model, text to image generation model that can follow the prompt very accurately. So that's one key finding that we probably need a very, if we want to very control the text to image generating model accurately by the text, then we need to have a very good quality text in our dataset. So this may seem to be obvious, but if you really didn't try it to do the experiment, you can never sure about it. So I think this result is still very useful, and we should appreciate this result. It's go investigate in the dataset. Remember, the dataset is a very huge dataset that contains at least several millions of image text pairs. But it can So it is not that obvious that the text is not really good because you probably need several um if you are downloading a dataset with like 500 million images, it really depends on the resolution. But if you are downloading something like 500 million images, you probably will need tera 1 terabyte storage. So typically, if you need to download like 1,000 images, 1,000 million images, you probably need 2 terabytes. So if you are downloading 1 billion, you will probably need 20 terabytes of storage if you keep them high resolution. So you can imagine there are a lot of storage is required and allow a lot of image. It is very difficult to actually look through all the description and all the data. You probably don't have enough storage for your PC to store like 20 terabytes of images. So it requires people to actually do something to see how bad or how good the image is. The text or image quality it is. So it hypothesizes that the current image model, text to image model, doesn't do that well to follow the text problem. It's perhaps because the noisy and inaccurate image captions in the training dataset. So that's a very reasonable assumption. It just need time and to do things to verify this assumption. It turns out the Darcy proves that if we simply clean up the data set, we can solve most of the issues. So this is one of the results. It provides a lot of different results, but I just choose one of them from the paper. This one is an illustration for this is the prompt. This is the prompt. You can see that it contains a very deep detail description, like the moon, a young woman with very red hair, you can see, and a sophisticated man wearing a sharp suit. A lot of different description. You can read the description and you can see there are a lot of details in this image. It contains, comparing to other AI generated images, this one contains a lot of details. And I'm assuming these details are corresponded to the text description because this is one they choose to put into the paper. But this one shows pretty well what they want to achieve and they can achieve by their model. So the trick they did is to use the model, a text caption model, image caption model to recaptioning the images in the dataset. As I mentioned, that in early years that we don't have the ability to do so because there was not so much image caption models available. But right now we have a lot of different text to image caption model or multimodal models that in our disposal. I'll show a list of them in very short. But just that we have these tools available right now. So we can use them. But there are still some point that we need to address. One is that what is our goal? What kind of caption that we are asking? So here list a few checkbox properties that we wish our caption to have, so that we can use it to generate the the images, to train a text to image model. So here are something that is not exist or overlooked in the original dataset. So we usually, when we ask people to describe an image, people usually describe only the main object in the scenes. So usually we didn't. We also usually like people in the photo or some main object in the photo. People doesn't really describe it in detail like the things in the background. So that's something that usually omitted in the text of the dataset, because so think about it, if you're asking to describe image, you probably will start with the most focus or main object in the images, something you are take it for granted. So if a car is running on a road, you probably just say the car, and maybe you are saying the road, but you probably will ignore the background, like the passenger. I mean, the pedestrian on the sidewalk or the house or the stop sign or things or traffic light. You probably will ignore all of these things. That's normal, but when we wish to describe when we wish to build a dataset for text to image generation, we probably want this sort of descriptions. Another thing is like the color or position or the size of the object. With a man smiling in the photo, we probably just say that. We probably won't say it is like the man is like the width or the height of the man, or maybe what he was wearing. Those kind of details. Usually, we are not describing the text on the object, like what is writing on a bottle or what is writing on a cup. So that's the things that might be missing in the data set that we wish to include it in. Okay, so then how do we actually do that? We train a model to do exactly what we to fill in these detail. So here are some example of to illustrate the things that we are talking about. So here are three images. The first row are the text that existing in the dataset. You may see that this, I think they are picking some really bad descriptions, like this one. This this one is in the dataset. This one is really bad. That's, it has nothing to do with the contents of the images. And this one is definitely not what we wish to have. and this one is has a URL or something. All of this is not related to the content of the thing. But even if because this one is a particularly bad text in the dataset, there's something more relevant, but still not good enough. So here are some descriptions that's generated by typical image caption models. Typical image caption models generate short description, like this says: a white modern bathtub sits on a wooden floor. This is correct and seems good. But if we wish to use it as a text prompt in the text to image generation models, we probably need something like this one. This luxurious bathroom features a modern freestanding bathtub in a crisp white finish. The top sits against a wooden accent wall with glass-like panels, and a lot of something like this one. You get an idea, and we have things similar to this one and this one. So perhaps not every image caption model can be work off the shelf. So we have to do the fine tuning to ask the image caption software, image caption models to generate things like the last row. So that's the idea. They use this kind of thing to fine tune to or image caption model to generate more this sort of things. They're using a method called COCA, contrastive captioner, to do the training. We'll talk about the multi-modal models in next week. But this is the idea. We're using a transformer. If we don't have this FI, then this one is the typical transformer GPT-like model. This big capital C theta is the parameters, the trainable weight. And we're using the previous tokens to predict the next code token and compute the log likelihood. But for image captioner, we are still training an image generation model. Text generative model like GPT, but we have to include the information of the image. So using a clip or some models like that to embedding the image as a prefix or tokens compatible with the text tokens. Then we can use these tokens to generate more tokens and generate the description of the image. So that's the basic idea of a multi-modal model. We simply embedding the images with the text tokens. We'll talk more about this next week. But you can see that there are currently a lot of multi-modal LM models, including the recent that is released or published this yesterday, mostly yesterday, the GPT-4o and a few Google models. Because today or maybe yesterday, depends on what time zone you are in, is the first day of Google I/O. So Google I/O announced a lot of models, including the low latency model, the small, I believe it's Gemini Flash or something. But they also include a lot of capabilities to ask the large model to understand images, videos, and all of these things. Same as GPT-4o, it has a capability to understand video images. Although it only take like 2 to 4, it suggests that we only use like two or 3 or 4 frames per second. It doesn't cannot accept image with too many frames per second. It only can take it like 2 or 4 frames per second. But it can understand the video directly, and it is end to end. I mean, GP4O. One of the sell point is that the GP4O is end to end. It can take the audio directly and output the audio. I'm not sure it is the model level or application level, but it's selling that it can take the audio input and output the audio output directly to do the conversation, and you can actually interrupt it at any time, just like conversation with human being. So anyway, these are some popular multi-model large language model comparing to other like a human expert. So this one German this is a leaderboard, but you can see the star here. You can see a star. Star means the number is provided by the author. So we are not sure how good it is. There's always some concern that the author is kind of biased towards their own models. But some models are not released and very difficult to do a test. So they still included the numbers. Just get a small remark that the number is provided by the author. You can see many popular models like Gemini Ultra, Cloud 3 Opus, GPT-4 Vision. All of these three are very commercial models and popular models. And yes, some other models. For the open source models, yeah, Fila 1.5, InternVL, and the Lava. I'm not familiar with the first two, but I would definitely try the first two and see if they have corresponding published papers. But Lava is a very popular model that is modified or fine-tuned from the Llama model. And some other very popular models include, you can check, I have put the slides on our course website, so you can click it to see the slide. And you can click this link to go to the full list. Some other popular models are Mini GPT 2, Mini GPT, Mini GPT V2, and Mini GPT 4, and Cog VLM. But when I see this leaderboard, they are very near the bottom. It doesn't seem to be performed very well. And there are also Lava 1.1 or 1.5, I don't remember, but the lower free version of Lava. And according to this leaderboard, the Lava 1.6 seems to be a huge leap from the previous version. So I'll definitely try it. Okay, so there are a lot of multi-model model available today, but they were training a model by themselves using the method called the COCA. I didn't cover this paper because we already have too many papers need to cover, but you can check this title and find this paper, and if you are interested in how to do that. We'll talk about multi-model, especially about the Lava models and Mini GPT models and Cog VLM. perhaps we are going also talk about the VLAN because like I said, I will definitely look into these two these two models, and we're going to talk about the clip, blip, and instruct blip. You can also see the instruct blip in this leaderboard. Okay, so what we are talking about mostly for the data preparation, for the data processing. That's only part of the recipe of a CL Diffusion 3. The major, two major highlight in the architecture, in the method that used by Stable Diffusion 3 is one of it use the flow matching method instead of using the classic, how we can only call it classic or standard or traditional uh, denoising diffusion model. It using the flow matching method. And the other is instead of using the attention U net, it's using a transformer based model. So that's the two part. These two are a little bit more complicated. I'm trying to summarize it in a more simple way, but still they are more technical compared to the previous one. Previous one, you are pretty easy to imagine what they did. They just clean up the dataset. One is for the image, the other is for the text in the dataset. And also, one key observation is that if we increase the channel of the autoencoder, it will improve the quality. That's it. But right now we are talking about more details about the mathematical formula or architecture of the models. So let's begin from the flow. Recall that we covered one good thing that we have already covered it before in previous lectures, the generative flow. So recall that we covered generative flow before, like especially for the FF hold. Like I will probably mention that in the course in previous years, this is one of the homework that to use the flow model to especially FF hold to transform one image into another, and we treat the image as a distribution. So we are talking about the same thing, like the flow model. Instead, we are not using just like the FF hold. We're talking about a continuous flow. So it has a name called the continuous normalizing flow. We are starting with one distribution and transform it into another one. So here is a comparison of the continuous normalizing flow with the discrete normalizing flow. So in the generative flow method we discussed before, we need some spatial architecture so that it can be invertible. And another way is to make it continuous. So we treat it like a differential equation, ODE, ordinary differential equation. So we can use any, we have more freedom to choose the architecture to model it into a differential equation system. So the word continuous normalizing flow comes from the paper, one of a milestone paper called the neural ordinary differential equation. The main contribution of this paper is to provide a method so that we can treat the um, we can do a back propagation on the ODE and using only the ODE solver. So this one is the algorithm. So by considering the ODE, the differential equation, we we can actually do the back propagation on this ODE process. So that's the main contribution of this paper. However, although this method is pretty good, I mean pretty elegant, because we can use any ODE solver. Because the main idea is that we translate the back propagation into another set of differential equation. Then we can use any ODE solver to solve that equation system, differential equation system. And if we solve that one, we are getting the gradient. So we can get we can do the back propagation. So that's a very elegant and very good method. The thing is, it takes many computational power, especially when the model is getting larger and larger, and we have a lot of data. When we have a lot of data, it is computational intensive. So we're still getting using the idea that we treat it as the flow as a differential equation, but using another way to solve or to find the to solve the issue using the neural network. Okay, so let's get some basic idea and object of the sorry. To in order to describe the idea, let me first get some basic object of the in description of some or definition of some basic object. So the basic idea is we just like a diffusion model, we wish to transform normal distribution, a random, totally random, pure random noise, like a normal distribution, to the target distribution, like the image distribution. We want to transform one thing to another. We just formalize this idea right here. So suppose we have two distribution. P0 and P1. We want to find a path between P0 and P1. So we call this guy the probability density path. Probability density path. What does it mean? So let's begin to look at what is a probability density. Probability density. You can see right here. You don't need to see the 0, 1 because 0, 1 is according to the time. When the time is 0, 1 means the all numbers between 0 and 1. This is not a set, not a list in Python. It is an interval from 0 to 1. This is a mathematical notation, not a Python notation. So this one is according to the time. So by the time changing, we are going to change a probability density from the P0 to P1 when making a transformation continuously. But before that, let's first check what is a probability density. A probability density is simply a function from the elements into a real number. A real number should be something between 0 and 1. The probability should be between 0 and 1, but the density can be over 1 because at a very small region, it can be very high. but it just need to be a non-negative number. We're mostly thinking about the positive number, but in definition, it actually need non-negative is good enough. However, because 0 causing some issues, and we can always replace 0 by a very small number. So here we are restrict us only mapping the density into a positive number. So basically, a probability density is simply a function to a positive number in one condition. If we integrate them together, all together, it should be equal to 1. So because the total probability should be 1. So in probability theory, we consider events. Event is like a subset in this space. So we can ask the probability of how much this event happen. What is the probability of this event may happen? So for example, for this image, because this one is a two-dimensional space, so this two-dimensional space is our space. In this case, the d is equal to 2. You can imagine that you are rolling 2 dice, and these 2 dice doesn't only return for each dice. The dice doesn't return a number from 1 to 6 like the normal dice. It returns a real number. So the first dice return a real number like 90, between something like 80 to 120. So say some real number, and the second dice returns some real number between like something like 0.1, 0.08, or anything along this y-axis. And these 2 dice are not independent. You have to throw them all together at once, and they are not independent. So the value you get from the first dice is correlated with the second one. Just imagine something like that. You simply get 2 numbers. These 2 numbers are not totally independent. They are related, correlated. And we can have a density function. So you can ask the probability of what is the chance that we the first dice got a number that is greater or equal to 102. Let's just say greater or equal to 100. And the second dice is greater than 0.1, greater or equal to 0.1. You can ask this type of question. So the probability density can answer your question. We simply get the region here. Greater 100 is this region, and greater than or equal to 0.1 is this region. So the intersection of region is like the upper right corner of this rectangle. So we do the integration on here, and we got a number. This number has to be less than 1 because the integration of the whole area is equal to 1, and everything is positive. So the integration of this one is strictly less than the whole area. So it's something between 0 and 1, some number between 0 and 1. So that's a density function. And what is the density related to the probability? Intuitively, you can think the density is a continualization of the probability. It's just because we have to actually get a number, we need to do the integration. So if you just pick just one single point, the number doesn't have much meaning because it's just a density. If you want to, it doesn't actually correlate to the probability because it's just the density. If you want to get the probability, you need to have to do the integration on the whole event. Okay, but anyway, this one is a density. A probability density path is something that connected to two different probability density. So when we say probability density, we are thinking about the probability. It's just we are going to describe, when we wish to describe this probability distribution, we are using this density to describe the distribution. So sometimes they are the same. Sometimes we are more focusing on the representation of this probability. So otherwise you cannot see what the probability is. So the probability density function is something you can see what the probability distribution is. It's just one of the representation of the probability distribution. And we are using a function to describe it. And this one is a graph of this function. They are different objects, but we're using one to describe another. So suppose we have this one is P0 and another one is P1. So at each time point, so at the time 0, we are start from this one, and at time 1, you cannot see it. I don't have a picture right here. It's difficult to find a picture like this one. But you can imagine we have a different distribution, different density graph right here. So just imagine it transit from one to another smoothly. We are most talking about, we haven't talked about how smooth it is, but we probably mostly we wish it to be smooth. So you just imagine it kind of changing it smoothly, sort of like something you can see in the weather report, like the temperature changing time by time, or like the typhoon is moving from east to west. It got a path, so you can see the picture is just changing from here to here. So I imagine the transformation from here to another distribution, sort of like this one. We start from this kind of a thing and gradually changing it to this kind of thing, or from this guy changing it to this guy, gradually changing to this guy. So that's what we are imagining the probability density path is. We're especially going to call the probability density path because we're going to describe it in the density form, and density can be described as a function. So if you go back to see here, it's kind of really clear. We are just providing a time step, and we are getting a RD to R function. RD to R is a mapping like this one. You imagine RD to R is something like this one. So given any t, we are getting this one. And the thing that this one is also a function is, if you give any point or element in this RD, in this case this R2, we can get a number. So that's all. So after we get this density path, probability density path, we can do the differentiation respect to the time. So we can get a time-dependent vector field. So just like the probability density function, a time-dependent vector field is a vector field that changes by time. Okay. So what is a time field? What is a vector field? A vector field is a RD to RD function. So at each element, we are getting a vector right here. So this one is R2 to R2. So the first R2 is each point on this square. And the second R2 is the arrow. Because this arrow has a direction and a length, so it is a 2D element. Because it's a 2D vector, it direct to it has a x component and y component. So that is a RD to RT vector field. And we add a time, so at each time we get a vector field. As here we didn't state the smoothness of the vector field, so this vector field doesn't require to be continuous. But we are mostly imagine or wish to have or think of is the smooth one. That is, it is changing gradually, continuously. But simply from this one, it can be arbitrary. Okay, if some people will get confused or stuck right here because you cannot imagine what this vector field is. So how do we get this vector field? How do we get this probability density? Well, not. It is like the shape or the type of an object. If you are familiar with programming language, right now we are merely talking about the type, what type it is. Like it is an integer, it is a string, it is an array, a 4x4 array, it is 5x5 array. It can have a different value. An integer or a float number can have any possible values. But we are talking about, we're just describing what the object we are talking about. Of course, there are some examples that we are thinking in our head. For example, we are wanting the P0, either P0 or P1 to be the standard normal distribution in this case. And when talking about the vector field, we're thinking about the differentiation of this guy. By the time. But what we were talking about is just a description or the specs of the object is. It just we have many examples. Just like we are talking about an integer, you probably will think about a lot of examples like 1, 2, 3, 4, 5, 100, 1000, 1001. And when we talk about a floating number, you have to think about some real number like 0 0.5. Typically, all 1, 2, 3, 4, 5 are all real numbers, but you were probably thinking about, okay, since we are calling about floating numbers, probably 0 0.5 or something, or 0 0.1, something like that. When you talk about a string, you are thinking about some text string, kind of like that. So it just, people are not, if you are not used to this mathematical object, you will feel like uncomfortable or, but the things are, they are just a description. We're not yet getting the value of it. And most of the time we are going to train it, so you don't need to worry about the exact value of it. It has. All you need to do is to have a visualization or imagination of what it may look like. And we, although we are thinking about high dimensional things, we are mostly thinking about the two-dimensional things like this one, or this one, or this one. Okay, let's go ahead. Oh, another thing we need to consider about is the flow. It is a path that on a vector field. So suppose we have a vector field, we have a flow right here. Oh, so this one is a flow that it In this case, it's a little bit different. So we'll see right here. So what is exactly the continuous normalizing flow is? So we have a simple, imagine right now we have a simple density P0. We may change it to P1 and so I get a reverse normalizing flow, but for now we are fixing it to be P0. Suppose P0 is a pure noise. When we say pure noise, we are mostly thinking about the standard normal distribution, multidimensional standard normal distribution. We wish to reshape this P0 into a more complicated one, P1. So we are using these things to push it to P0. And the phi t is a flow. And let me close the camera. Okay, so we're using this symbol to say we push this PL to PT by using this flow. This flow is related to the field. This flow is related to the field, time-dependent field. We are following this field. So at each time we get a factor right here, and we follow this factor as our tangent. But the time is changing. Unlike this one, the time is changing. So like this one, this curve is at least each pixel, the tangent is the vector on this vector field. But since we have a time-dependent vector field, so when the time is going, the vector field is moving. And these two are just has a static vector field. So the flow itself is simply a curve that at each instance, the tangent is coincident with the vector field, the vector on the vector field, on that pixel, on that element, on that position. So we have a vector field. Suppose we already have a vector field. So start from each time 0 or any time at each position, we can follow the vector field to go ahead. And we can form a curve. That is the flow. That is the flow. So phi is the flow, and the t is at the current, at the flow at that time. So we start from one point and follow the vector field. Follow the vector on the vector field as the speed. So we can move ourselves to a new position. Start from time 0 to time 1. So that is phi t. So the phi t is define the path from time 0 to time 1. So start from a position to another. But we are more talking about the probability density. The phi t is simply describe the movement of the position from one to another. So it describes the RD itself. It describes the at each time. Where were we at each time? But we can use this one to apply it to the probability density in a more apparent way. So write in this formula, in this notation. To be exact, what we are doing right here is like this one. So we already have a P0. We already have a P0. P0 is so as it mentioned, you can consider it is a standard normal distribution. So suppose we have already the vector field and the flow. We got that vector field and the flow. What is the transformed or the morphed probability density at the time t. Recall that we describe the probability density as a function from Rd to R. So all we need to ask is what is the probability density at this position at time t. So the position is x. So recall this one, these two whole this formula is just denote the probability at time t. So we ask the density at this x. We simply pull back this x to the original start point. So suppose this one is the path. Right now we are here. We are pulling back to the original point P0. And we ask what the density it is. But because the size of the it's getting morphed. So maybe you can imagine one transformation is to enlarge the whole thing. So or maybe it is shrink things. So at that, although we can know the density at this point, but we cannot directly use it because the area around it may be expanded or squeezed. So we need to know the deformation about the space. So does the neighborhood is getting enlarged or squeezed? We can know that by using the derivative of this by x by computing this one. This one is the Jacobian. Sorry. The Jacobian matrix, and we by computing the determinant of the Jacobian, we get the scale of the scaling factor of the areal change between the PDL and the PT. Okay, so these two put together, we can get the corresponding probability density at time t for this point x, for this position x. So that is the simple description. But basically, you just imagine that we have a start with any distribution. In our case, is the pure noise, and we have a vector field. We can move the distribution at any point of time, any point and at any time. We can transform it to a new distribution. And the transformation that you were thinking about when we describe in mathematics, we can write it in this formula. And we have several concept terminology according to this. Similar, but a little bit different. Let me summarize it again. The phi is the flow. The p is the distribution. So when we have a vector field and start from one distribution P0, and we can move and reshape this original distribution into another by time, and because we can get a flow, and we can use this flow to describe the new distribution PT. And that we say the vector field Vt is generate the probability density path Pt if it satisfies these things. It only describes the most apparent and obvious transformation. And because it is described it in mathematical way, it is very accurate and specific and clear. So we know everything about it. And because you can see that Vt is sort of like a differentiation, so we are mostly thinking about the if you know what the differential equation is, it is pretty much the same as a differential equation. Because a differential equation is at least for the one first order equation, differential equation, is that we know something about the gradient. We have a function. We have an equation of the gradient and the position itself. So we try to solve the position. So like if we know the speed of an object at each moment, we want to reconstruct the path of this object. So that is a typical, or probably the first several differential equation you see in when you study the differential equation. This one is pretty much the same. It's just that we corresponded it with many different start point, because phi is not only consider just one start point, we consider the whole start point, and we connect it with a probability distribution, because we have changed the event space. Okay, like we said that ODE can solve this one, because this one is simply a differential equation. So neural ODE, we can use the neural ODEs to solve everything using the differentiable ODE solver, but it is very computationally expensive. So we wish to find a more efficient way to do that. So in fact, instead of solving the equation itself, we are solving just like the diffusion model. We are solving the gradient. We simply solve the gradient, and the idea is like we don't need to solve it. We solve the gradient, and using a similar method, we can sampling the whole distribution, just like a diffusion model. So we regress the vector field and generate the probability path. So that's the idea. So here are more notations. Given x1, we can define the conditional probability path. So like we said, the difference between the path and the flow is that when we consider a differential equation, we usually consider a single initial condition, and we consider a path. So if I tell you the start point of an object, and I tell you at each moment, at each time, the speed of this object, we can reconstruct the path, the trajectory of this object. That's easy. But for the normalizing flow, we're considering every single star point, and we're considering applying this to lift up this transformation to the probability density space. So that's getting it more difficult. But if we are considering only one star point, that's it. We are considering only one point by given star point x1. Then things get easy. Because everything is just like we are start from one initial point and get that single path. And if we wish to go back to the probability, we are integrate every single path according to the probability of x1. But here it is because it is x1 and on the q, and we are treating the q. Q is the target probability density. So we are more like the terminal condition, not the initial condition. We are more in this one. Literally, we are thinking more like the terminal condition, not the initial condition. But things are pretty similar. So the idea is we can consider the conditional probability path. That is easier. We consider one path at a time, and then we integrate them together by the probability. Then we get a whole picture. So the marginal probability path is this guy, and simply basically we are talking about the we know we are going to end at x1, or the terminal condition, not the initial condition, and what the path it is, and we are also considering the probability along this path. Okay. By a similar method, we can define the marginal vector field. So from this integration, it is similar, although it is not apparently obvious that this one is corresponding to the vector field generated the marginal probability path, but it is. It is. So the marginal vector field generated the marginal probability path. This formula is easy to see. It is because we are actually, this one is the probability. When you think about this formula, you think a fixed t and a fixed x, because we are given t and x on the outside. Well, I should put it right here. We are consider fixed t and fixed x because t and x are given outside right here. So t is given, x is something we know. So how do we actually compute the marginal vector field? This is just the weighted sum of different terminal condition, or maybe if you consider reverse, it is the initial condition, but we are reverse it, so it is the terminal condition. But it's just a condition. So we are weighted sum of different condition of this this vector. This marginal vector field is the considered as a weighted sum of different conditional vector field. And this one is simply says that we given ptx, what is the probability of given x1, and we are reaching here, and it is also x. So ptx has a lot of different. So when we get the position x here, it can come from different start point or different condition, like the terminal point may be x1, or maybe other values. So are picking only the values. When this can be considered as the joint density. So we are ending at x1, and currently at time t we are at x. So this one is the probability. So we're using this as a weighted sum, then we get the marginal vector field. So in fact, the marginal vector field generates the marginal probability path. So that's a good thing, and this requires some computation, but this is a thing. And after we get the marginal, suppose we get the marginal vector field, we have a flow matching objective, so that we can get the flow. We can get the flow at each time. So simply, the flow matching objective is the square error, the mean square error. So this one is the mean, and this square error. It's only that this one is very difficult to compute. It is invisible to compute, to be exact, because UTX very difficult to compute like this one. So if we wish to compute UTX, we have to do the integral over all different all possible x1. So especially if you have a really large data set, it is difficult to do the actual computation. If we want you to compute this one, we have to compute this one first, then use VTX to minus this one, and to do the square. But the good thing is, although this one is not directly a summation, but the square it usually look just like the variance formulas when you derive, we can expect that this one should work pretty well. So in fact, one of the result is that we can, instead of computing the fraud matching objective, we can compute the computational fraud matching like this one. So for this one, we have to compute everything and sum them together. But for this one, we don't. We compute the conditional one only. But it turns out their gradient are the same. In fact, they are only differ in a constant. But because we are only interested about the gradient. So okay, so this one is pretty much the same. I mean, we are only interested about UT because VT we need to approach to UT, and we are using a gradient descent, and their gradient are same, so we can optimize them in the same way. So that's a fraud matching thing. So let me summarize a little bit. The idea is that, like the neural ODE, we are considering continuous normalizing flow. But if we're using the method of a neural ODE, it's kind of difficult to computational expensive to actually do the optimization. So we are learning from the diffusion models to do the similar thing. We only compute to approximate the gradient. And after we get a gradient, we can sampling the whole things, just like the denoise sampling. And after we do some computation, we know that we can, by the first theory, the marginal vector field is just can generate the marginal probability path. And so we can use the fraud matching objective to do that. But this one is very difficult to compute. And we find out because we are only work for the expectation, and we are only work for the square, and they have nice property. So the gradient of them are the same. So only need to optimize the conditional fraud matching objective. And this one is doable because the conditional probability path, the probability conditional probability path is more easier to compute. So all we need to do is to do the conditional floating match objective, train the model with computational floating match objective. So we are training the VT here. There's a parameter we didn't write here, theta. Suppose there is theta behind in this formula. We are training VT according to this guy. So to specify, if we are considering in general, so if for PTXX1 is something like a normal distribution, it doesn't has anything to do with the distribution of x1 because we have already fixed x1. So we are assuming that when we give it x1, ptx x1 is a normal distribution. It's a normal distribution. The mean and the standard deviation is something that we can train or we wish to train for. So this is the mean and the no, sorry, this one is something we predefined. That we predefined. The only thing we don't know is the distribution of x1, but we can define some way, so which we will specify later. But we're going to define the mean and the sigma t, and preferably that we wish it has certain qualities. For example, we wish to mu 0 x1 to be 0 and the sigma 0 x1 to be 1. This is because at time 0 we wish it to become a pure noise. So it is centered at 0 and has become a pure noise, standard deviation. And when time is equal to 1, we wish it to center at x1. And it has a very small standard deviation. Probably 0, but 0 doesn't work very well in many cases. We wish it to have a very small standard deviation. And we can define the mu t and the sigma t explicitly in some way, but we want it to satisfy these two conditions. And suppose we already have this one. Suppose this one is none and this one is none. Let's define this psi t to be this guy. This x is some noise. X is the standard is just a noise because we define right here. It's a noise. X is just a noise. We let this one here, and we can use our notation to lift the things right here, and we wish that because we have very small standard deviation and mu 1 x1 is equal to x1, so we wish when the t is equal to 1, it's very close to q, and when t is equal to 0, this guy pt is equal to the pure noise. So that's the idea. But we can have a different way to define the mu and the sigma t. The thing is, suppose we already define the mu and the sigma and define the sign in this way. And we mostly wish this sign to be some fine transformation. And we can actually compute the whole things here. So there's another theorem. So we can compute the mu t according to all of these things. So that's how we compute the mu t. Actually compute the mu t x over x1. We still don't know the distribution of q, but we are kind of isolated that things out. So everything else we can compute, but we don't know the distribution of q. And then when we plug into the else the conditional from matching objective, we are trying to ask the model to learn the distribution of q. But everything else we can compute. Okay, so to more explicitly define the mu and the sigma, we have some example. For diffusion models, there are many different, we'll see something later. But one thing is that we define that it is the mean is x1 and the standard deviation is according to some scheduling. So we can model the diffusion model like using the above formulas, and we can compute the UT. I'll compute the UT using this formula. Got this. Although it's complicated, but we can actually compute it. So we can apply the flow matching objective to the diffusion problem. The experience in this paper says that they can get a more stable and robust result, although they are dealing with the same problem, but the objective can lead to a more robust and stable result. Another example is the optimal transport condition. It simply do the linear interpolation. So that is something we are using in Stable Diffusion 3. Stable Diffusion consider all these settings and a few more, but turn out this simple linear interpolation can lead to a best result. So by using a simple way, the linear interpolation, we can compute the objective, the conditional flow matching objective, and get this formula. This is the thing that we need to compute. It's easy, more easy to do so. A more easy formula, more simple formula, and leads to a better result. By comparing a diffusion objective, I mean the diffusion setting and the optimal transport setting, you can see the trajectory. This is an illustration of the different trajectory from these two different settings. They are similar, but the rectified or optimal transport things are more straightforward. If this if this is something you want, then you can use these two visualization to choose which one is better suited for your choice. So the paper compare different methods. So the first rule is the diffusion setting using score matching, and the second one is the diffusion using flow matching. If we simply look, you can see this one is a standard checkboard. Sorry, the checkboard pattern is one of the distribution that people use to calibrate or to benchmark their algorithm. So this one, the target is a checkboard. This is one of the difficult one. Yeah, usually we are getting something like a checkboard, but the square is not totally the edge of the square is not totally straight line, and there might be some something not cleanly separate. You will see something like here, mostly like this one. They connect to each other. So for me, the first two, the results are pretty similar. You can see a difference right here. But clearly, for the flow matching using the optimal transport, it will get the checkboard pattern earlier than at least for the formation method for diffusion setting. So that's interesting. So you can have some connection between this picture and this one. So this one is more directly straightforward to the goal. And match it to the beta scale, to the target scale. But arguably, at this one, you can see something. It tried to split the distribution into several. So maybe here are some attempt to match the trackball pattern. But definitely you can see that we have a small trackball pattern right here already. And this one we cannot say the same. Also, it also argues that the optimal transport setting is more. This is number of function evaluated because we already know the pattern itself. So every sample it can be computed from a function. So this one is more the sample efficiency. The argument is that you can see that this one already has more at the very low sample rate. I mean, for very low sample number, it already gets an acceptable pattern, while the diffusion setting does not. So in this experiment, it shows that the optimal transport setting might have more better sample efficiency. Also, here are some numerical results. Basically saying that the best combination is the from matching with optimal transport setting. So it is good in the negative log likelihood, FID, and NFE, a number of function evaluation. So here are some examples of score matching. Before we only see the toy example and some numerical numbers, but you can see here by your eyes to see that it converges more quickly when we're using the formation and optical transport, or we can call the rectified flow. Okay, so that was the flow matching algorithm. That was the more painful or difficult part. It is actually very good reading if you to read the paper, but just like other mathematical derivation in the computer science paper, if you read the main text, the derivation usually not that. This one is I think it is the this paper is the presentation in the paper, at least in the main text, is more mathematically clear than the stable diffusion 3 paper. But stable diffusion 3 paper gives more concrete way. It's just the formula in at least in the main text. I think the formula is more fake in the stable diffusion. The formula here is more clear. And you have to also read the appendix. But the appendix usually in the computer science paper usually provide too long computation. So you need to have some patience to read through the computation. Some of the computation are not necessary, and some computation steps jump too fast, in my opinion. But they are basically readable. They are almost readable and understandable. But just compare these two papers. I think at least in the main text, the presentation here is more mathematically preferable in this paper than the stable diffusion 3. But stable diffusion 3 has a very concise and short summary. So after you read this paper, you may want to check the stable diffusion 3, and it has a more to get a big picture. But some of the details you may want to check in this paper. But uh, you need to have some patience to read this paper. If you pass through that phase, they are quite interesting. But when we talk about and explain to somebody, it is a painful process. It's difficult to explain these things, but um, it is easier to read and compute by yourself. Do the calculation. It's not that difficult, but when you want to explain and listen, this one is very painful. So we are passing the painful section. We are going to a more non-painful section, easier section. This one is the architecture, the transformer architecture. So the main result is that by using transformer, instead of using the unit or attention unit block, using the transformer, a variant of transformer, the model, the diffusion model can get more scalable, have a better scalability, and more simple efficient. The result is very convincing and it's verified by the Stable Diffusion 3 results. So if I have to choose one, although I haven't do the experiment by myself, but I think I'm convinced that the DIT is a better architecture than the attention unit. So if I have to choose just one architecture, I probably will choose this one. If I have to choose one and cannot switch to another, I will choose this one. I think it's very convincing result. So basically, it just used the feature transformer, kind of adapt the feature transformer into use in the diffusion. It sounds like a pretty obvious or apparent or boring result, but if you really think about it, the most difficult part is to add the condition into the transformer architecture. And this is the main contribution. I mean, the main takeaway from this paper, along with the convincing experimental results. Okay, so let's first look at the attention unit. This one is used by the most latent diffusion models. So it is a unit, except that the connection, the skip connection, is replaced by a cross attention block. So that's the attention unit. Oh, that's the attention unit. This is used by serial diffusion 1, and I think it's serial diffusion 2 is also used this one, and used in the latent diffusion implementations and a lot of. I'm not sure about the DDPM, original DDPM, but at least a lot of implementation of DDPM is also use the attention unit. So this is unit with attention mechanism. Pretty straightforward and useful. So this one is the latent diffusion transformer. This one is the block. This one is the whole transformer architecture. So first of all, because we are still using a latent diffusion architecture, so we are getting a noise latent and output noise, just like the latent diffusion or other diffusion, we are predicting noise. And also we are considering the conditional denoising. So we are having an input of the condition. In this paper, it only consider about the class condition. So like in an ImageNet, we have a 1,000 class like a label, and also a time step. But I mean, in the Stable Diffusion 3, it consider the text prompt condition. But here, it only consider the label, the class condition. And combined with the time step here and do the embedding. For the latent noise latent, because latent is sort of like a low resolution image in a different color channel space, like we described it before. So it's, at least it is still a 2D with channel. So just like the VIT, visual transformer, we do the patching things. So at the beginning, it has already reduced the dimensionality into say like 32 by 32 or maybe 64 by 34 with 4 channel. Here it is 32 by 32 with 4 channel, and it do a patchifization to to find a small patch of this one and put it into a DIT block. So this one is the transformer block. And after the transformer block, it has a layer normalization and the linear reshape into noise and the sigma. Sorry. So this one is the block. So we'll see a little bit later, maybe how this block works. Maybe I will describe it later. So let's first talk about what is a visual transformer is. Because vision transformer is because this one is basically the vision transformer add the ability of adding condition in it. And it also considers several different ways to add a condition. It uses the ADA normalization, like the ADA in, but it is not instant normalization. It's ADA layer normalization here. Okay, so the visual transformer is proposed in this paper. Image is worth 16 by 16 words. I'm not listing, and I didn't list the author here because this one is a famous paper. You can simply search for it. So this one is the first and the most successful one so far by for applying the transformer on vision task. The key point is it use patch. It separates the image into different small patches. Previously, a lot of different attempt on applying transformer on visual task, but they get some degree of success, but none of them are declared to beat the convolution networks. But visual transformer is getting somewhere that can beat the CNN, convolutional neural networks. So the key idea is we are split the images into different patches. So one of the important things is that how do we add the position embedding? Because we know that in transformer, we have to have a position embedding. The thing is, here it uses 1D position, so it just treat the patches as a linear order. I think it is because it is only dealing with image with fixed aspect ratio and fixed dimension. It makes more sense to use 2D position if you are dealing with various different size of images. But here, I think it only use one dimensional embedding. But you can see in the paper, the difference are very little. So you can either way, but adding a position is much better than without adding position. Position is important. That is for sure. So basically, it's just a simple transformer encoder layer like this one. It has a norm layer. It original in transformer is a layer normalization, but you can use other norm like the square root norm or other normalization method, and the multi-head attention and a skip connection, a ratio block here, and the normalization and the MLP. You can replace MLP by a gated layer, like the one in Pixel CNN. You use a gated layer, but with different activation to replace MLP. But the idea is we have something like either a gated layer or MLP work component wise, and also we do a ratio block right here. So that's the idea of the feature transformer. It has three parts. First is petrification and using the position embedding, and it just put the transformer encoder here. So what's the difference between the DIT block and a transformer block in VIT? It looks a lot complicated than this one. But the thing is, everything added is simply modulation to put the conditional in. It's a conditional modulated, or as it's described here, it's ADA layer normalization. It is simply ADA layer normalization. So that's from start, step by step from start. The embedded patches and the input tokens are the same. And here it uses layer normalization. Here it uses norm. The difference is here they did modulation. So after using a MLP on the condition, it get a gamma and beta 1. So use this gamma and beta 1 apply to the layer normalization. So we simply change the scale and the bias to this layer normalization. This is as can be originally back to the style transform, the fast style transfer or instant style transfer. That's called ADA-in, and it is used in the style GAN. And the style GAN to modify it to modulate formation instead of using the ADA-in directly. But the idea is pretty much the same. We simply modify the things after we simply do a very simple modification, changing the scale and the bias right here, and we fit it. So that is getting a way to inject the information of condition into the whole flow, the network flow. So adding it into here to injecting the condition. Then we go to the multi-head attention. It's the same, and we do another round of condition injection. But this time we only have alpha to do the scale, not the bias, not the shift. And Similarly, we have a skill connection here, and another round of normalization. And after normalization, we have a scale and shift, so that we can inject the condition into the network. And we have a point-wise feed forward, like MLP right here. This MLT is also point-wise, but feed forward is a more big concept. It covers a larger concept than MLP. MLP is a feed forward network, but not every feed forward network is MLP. So it can be replaced by, say, the gated network, like we said before. And then the scale, we do a scale again. Like this one, we inject the condition again. And finally, we do the skip connection. So you can see, aside from the conditional injection using the modulation, or we call it modulation, or the ADA layer normalization, it is pretty much identical to the original visual transformer. But something you need to observe that is to appreciate this contribution is it is not that obvious because there are many different ways to inject the condition. Some of them are more obvious than the other, but there are many different ways. And even if we inject the condition using the modulation way, like here, there are many different places we can do. We don't have to. Do we have to inject it 4 times at each possible position? Or maybe we can just do it for 1 or 2. So that's an interesting choice. I would take that it performs better if we inject it everywhere. If it is the case that it is also aligned with the discovery from the StyleGAN 2, because or StyleGAN 1, I'm not sure, but at different stage, it can provide different meaning, different part of it. It can use employ different information in the condition. So if we only inject at a very early stage, it may only work on a very high resolution level and may not work on the detail level. So, but anyway, this is a choice of the design of the DIT bug. There are other ways to do the conditional injection, to inject the condition into the network. Like we can simply do the concate it with the input token. That's one way to do a condition, a very popular way. I think they have already tried it, but choose the previous one. And another popular way to do that is to do the condition with cross attention. So because we have a multi-head cross attention here, multi-head attention here. So maybe we can put the condition as a value and the key, and then so maybe we have another round of attention, or maybe we have a single run and concate all these things together. So they can provide a wider range of choice of value and the keys to do when we do the attention. Okay, so those two are both reasonable choice for decide how to inject the condition into it. But it turns out just like the StyleGAN and many image generation models, it seems like the modulation way seems to be very good choice. for injecting the condition into a generative model. But I think there is no thing to prevent you inject it into multiple purpose, like combine all these things together, or at least combine the cross attention with the modulation. But it's just it simply using a modulation, it works very well. Sorry. So finally, we are going to talk about the Stable Diffusion 3 paper. So basically, it employs all the techniques talked before and has certain modification and variation on its own. So for the flow matching, it has a approach. The text it describes the flow matching. It's the other way around because P1 is the pure noise, while P0 is the target things. It uses this way around, and it write the formula at the very beginning using a linear formula to frame the whole framework, and do not attempt to cover a more abstract way. Okay, by the way, let me go back. Something I forgot to mention. That is important thing. Although I was mainly talking about the flow matching paper, this one, a lot of there are 3 papers talking about pretty much the same thing. Very similar discovery in these 3 papers concurrently. They are mentioned and given a different name. So in this paper, it gives a name flow matching. It focuses on the flow matching method. And this paper is called rectify flow because it is more focusing on the rectify flow part, like the straight line between the target and the target diffusion and the noise. It's focusing on this one. I haven't looked at this one, but from the title, it seems like it also emphasis on the interpolation of the target distribution and noise. That's my impression. But all these 3 papers are introducing similar discoveries at a similar time. Okay, so let me go back to the Stable Diffusion 3. So the Stable Diffusion starts from the interpolation directly from X0 is from the target diffusion, and the epsilon is from noise directly. But the P0 and P1 are the other way around compared to the flow matching paper. And it uses the terminal condition as well, but it is on the noise part. However, the whole technique are pretty similar, and the results are pretty similar. If we get the formula here, or D prime T is the flow we wish to get, the conditional flow right here. You see conditional on the epsilon, and we can get the formula. So if we have already specified is A and B, then this one is the formula. And by introducing a new symbol called the SNR, signal to noise ratio. Because you can see that A is the strength, the scale of the signal, and because epsilon is noise, B is the scale of noise. It says how strong the noise is and how strong the signal is. So the ratio between A and B is can be considered the signal to noise ratio. So consider a symbol called lambda. This is the signal to noise ratio taken by log. So we can simplify the formulation here to become this one. So we only get the Z and the Z epsilon and the SNR, signal to noise ratio. Here. Okay, so the conditional flowing matching objective can be write as this formula. And consider the last one. This one is the thing we wish to learn. The UT it's called the phi theta. It's a model. But by transforming it a little bit to rewrite it in some other way, you can write it in this form. We still want to learn something that is close to the noise, or we still want to use a model to predict the noise, and we have some weight right here. So our goal, the final objective is the same. It's only right here. This one can be considered only the weight. So we can write in a more universal way, like this one. Unified way like this one. We keep the signal to noise ratio, and everything here is considered as a weight, and we are trying to predict noise. So in this method, in this way, we can unify everything together, including the classical denoise diffusion model, denoising diffusion model. So can compare everything together. So in stable diffusion, it considers a lot of different settings in this form. So we have a lot of different variants. So one is the rectified flow. So you can see that it includes 3 papers, but the name is come from the first one. All of these one are pretty much from the same time and similar results. So it includes all 3 of them. So we put a straight line between the. So this one is a linear interpolation. We put a linear interpolation between the image, the target, and the noise. And by computing the above computing, we can get a weight like this one. Your weight is simply look like this one. 1 minus t over 1 minus t. That's the most simple one, and this one turns out to perform better. And we also have the EDM. DM is stand for diffusion model, and the E is equilibrium. So this paper search different parameters for better parameter for the hyperparameter for the diffusion model, for training diffusion model. So you can see this one is look like this one. Dt is equal to x0 plus bt epsilon. This one is the one without a factor in front of x0. You simply put the x0 right here and add noise. In previous, we have a combination decaying, which we'll see it later. But this one is a formula that we simply add a noise. And that paper says, oh, okay, this one works good enough. And simple. This one just works. So in this formula, we can get things like this one to be W. And also another paper, this one I haven't aware of, but apparently you can do a useful combination using the cosine instead of a straight line. You use a cosine. It's still like because when t is equal to 0, this is equal to 1, and this one is equal to 0. And when t equals to 1, this one is equal to 1, and this one equal to 0. It works kind of like the interpolation, similar to, at least for the start and the beginning. They are at the start and at the beginning. They are look like the linear interpolation. It's just they are more smooth. So this is another way to do the interpolation. So they consider this one also. Okay. And finally, in the latent diffusion model, it considers the linear scheduling it can put. So that accuracy will have some alpha and beta. And in the DTPM and the LDM, they have some small variation. So all of these can be computed. In addition to those settings, in Stable Diffusion 3, it introduced a more free form of weighting. Modify the weighting to the previous one, mostly for the rectified model. It adds a spatial weighting on it. The reason is that the prediction is more difficult in the middle, in the t time scale in the middle than in the end, because at the end it is mostly none. We know the gradient. We don't know the distribution at the Q part, at the target part. In this case, the P0. We know everything about it at P1, but for gradient, we know both parts. for the conditional flow, but in the middle is more difficult. So it wish to add some weight so that we can sample and train more on the middle part, on the intermediate part, on the intermediate time steps. So we can sampling them more frequently. So it uses some weight that is more heavier in the middle and more sparse, more little, small on the both end. So one method is use logit normal sampling. It basically is a normal diffusion, but it shrink the domain from the whole real line into 0, 1. So you can see that there is a mapping for t into a small area. That is log 1 minus t, t over 1 minus t. It has a singular point at 1, because 1 minus 1 is 0, so we have a division by 0. And also t is equal to 0. The log of 0 is negative infinity. So this is a function only defined between 0 and 1, not across. But it can map it into negative infinity to infinity. That is whole real line. So it is a modification. You can see a domain adaptation of the normal distribution. So of course you have to adjust some constant so that the integration have to be 1 over the whole thing. So this is a graph. You can see that when the mean is 0, it is look like something look like the orange one, and you can change the mean. This one is the mean is 1. The above the mean is 0. On the below, the mean is 1. Although we call it a mean, it doesn't map to a mean. It is legit map to a mean, to the 1. So you can see the mode has a different mode right here. It's not, but not the 1. However, for 0, the mode is at 0.5. Because no matter what the scale is, you put 0 in it, it will map to a 1, to a 0.5 for logic function. Okay, so anyway, this one you can see that we're mostly taking this guy or maybe this guy or maybe, but you can see that by definition, by the design, the density of is 0 at 1 and at both end. So density at here is 0 and the density at here is 0. No matter what the mean is or no matter what the sigma is, doesn't matter. It's 0. So that this change might be too extreme. We only wish to lower the density at each point. Although it may not seem to be immediately obvious that may cause any trouble on training, but that is a concern. So in this paper, it also consider other sampling method that has a heavy middle, but not 0 at each end. So this one called the mode sampling. So you can see on the left side is a mode sampling. Look like these guys. Typically in the middle one, because we want the intermediate to be sample more. And on the right hand side is the logit normal diffusion. You can see it's heavy in the middle and 0 on the both end. It also consider cosine map. It's another scheduler proposed in this 2021 paper. So it also consider this weight. Okay, so this one is this is the architecture of the stable diffusion. It looks intimidating because this is really complicated. But let me break it down a little bit. The middle is simply the DIT blocks that we mentioned before. We introduced the diffusion transformer block with some twist. And the twist is important. I will talk it a little bit later. But this one is the transformer block. So we still have in a latent diffusion architecture. So we have an autoencoder and get a noise latent here and do the patching because we are using the visual transformer. So we have to do a patching. And then we have positional embedding, like the visual transformer and in the DIT. And we fit it into it and get everything out. So that's the basic transformer part. The other part are conditional part. The other part are just simply condition. But for the diffusion part, it input the latent image, I mean noise latent, and get out output of the unnoise denoise things. Get a noise or the sigma, or maybe if we are working on the ferro part, so we simply output the denoise image. So this one is the transformer denoising part, and this one are all other things are the condition. So our condition start from here, the caption. We use 3 different text encoding model. So clip, G, clip L, and T5. Clip G is more smaller model, and clip L is a little bit larger, and T5 is like with Google T5 architecture. So this one is the largest one among these three. So there are two paths to add the condition into these DIT blocks. The first one is that, like before, we are passing it through an MLP. We're passing it through an MLP, and we add some position and time step into it. And we get the embedding, encoding right here, the text encoding. Very similar to previous Stable Diffusion. And we are inject this condition into the DIT models. Just like the what we did when we using the modulate conditional injection, like the ADA layer normalization, like what we did in DIT block. So that's the input. That's the same. But there's one more text input, and this one is total new. This one is totally new way to do so. So because this one is getting things from pooling, so this one has a lot of information is discarded. So Stable Diffusion 3 try to encode more text information into the model. So it put the clip L information here and the T5 information here, and to get a lot of token. You get a lot of tokens here. So this one is more work like an input of the transformer. So it also give this information, this condition into the whole DIT blocks, but it treat it as an input. Unlike the condition, we feed it into every step, and in every step we will feed it into a lot of different layer. After a lot of different layers, we continuously inject this condition. But on this route, the text information are become a sequence of tokens, and we are treating it as an input of the transformer, as a transformer input. So consider this transformer taking two inputs. The first one is from the text, and the second one is the image. So this is a single transformer that works on two sequences together. So this one is a detail of the the DIT block. The stands for multi-model. So not only it works for image, it only works for the text. So what we are thinking is that we have actually two separate. First, we just forgot about this one. Just think about this as two separate DIT blocks. So this one is an input context condition, the text condition. This one X is the noise latent, and perhaps the things from previous layer. But just the image part, you can see that is the image part, and this one is the text part. But anyway, they are just a sequence of tokens. And we feed it into the DIT block. So it's just a transformer block, but we inject condition at the various places. So these conditions are, we call that, although this one is still the condition from text, this one is from here, from the clip. And this one is from the clip and the T5 to form. But when we talk about text condition, we have two. One is text encoding, and the other is tokens. The other is tokens, and this one is encoding. So take the text encoding condition in the same way as when we do the DIT block, and works both for the image part and the text part. So they are basically the basically a separate process. At least after this one, it is totally separate, and at the beginning it is separate. But they are doing the attention together. Okay, so you see that we're doing attention together, but we're just two separate DIT block, but these two DIT block connect in a way that we're doing the attention together. Okay, so that's the way stable diffusion. That is a transformer block of the stable diffusion. So it's called the MMDIT, multimodal diffusion transformer. Okay, the interesting is the experiment result. It works on a lot of settings. It has 61 different formula. The experiment actually has two parts. The first part is just to find the best formula of rectified flow to refine the hyperparameter and the setting of a rectified flow. So in this part, it has 61 different formula and work on two data set. So they tune a good recipe of rectified flow. The second part is actually train the model in scale using this recipe. So only for the first part, it worked on two dataset, ImageNet and CC12 medium. The ImageNet is used for the class condition, and the CC12 medium is used for the text prompt condition. It has 61 different formula and tests on these two datasets, and with different sampling method, it has actually have 24 combination of sample settings. So it got a lot of different results. If you want to train it on a CC12 medium, on a say a 512 by 512 resolution, it is estimated you require about 30,000 US dollar, approximately like 1 million New Taiwan dollar to train it, and it train like 100 different variations. So it requires a lot of time and a lot of machines to do so. So the experience result is important because we are unable to repeat the experience. We can only trust this experience. So these are several settings, including both epsilon and the V prediction loss. So one is for the predict noise and predict the value, and it's like the different pi, different weight on the rectified model, like a rectified flow. And for EDM, it uses different settings. So these one are all the different settings that we mentioned before, and it specifies the numerical settings. And each one has different sampling method, and use it to compute the clip score and FID distance. So it's a default comparison, but it uses some algorithm to rank them from high to low. So the result is that with rectified flow and the log norm logit normalization weight with this parameter get the best result in general. You can see that this one has a rank number 1 after the first step. For first step, but in average, this one is better compared to all of these different settings. So it's a very comprehensive comparison. Right now, you can see the actual clip score and the FID distance. So for both ImageNet and for the CC12 media. And the conclusion is rectified flow with logic norm, and this one is should consider the best. Although in single score, it may not reach the top one. This four reach the top one, but this one works the best. And the EPS linear is the method used by the latent diffusion model. So this one can be considered as the previous state of art, or maybe considered as the previous version of the stable diffusion. You can see that this one works actually pretty well, but only the rectified flow method can defeat it. Other method cannot defeat it. So for example, for FID, it actually has the lowest of FID among all these other things. But the rectified flow with some kind of the norm adjustment can defeat it. But other method it tried, probably from other paper or from other popular approach, does not defeat the original latent diffusion linear schedule. And this is another plot to show its supremacy. So rectified flow is actually sample efficient. So even with less sample steps, it gets performance. The performance is better than other methods. So after they get a good recipe of the rectified flow, when do the real training, it combines the several different accomplished methods like the data processing and data filtering things like before. And this one is the improved autoencoder. So like the emu paper, it also used the 16 channel for the latent space. And the result consistent with the result of the emu paper. Although it doesn't use the Fourier future transform, but it used the 16 channel. It would be interesting to compare it with or without the Fourier future transform. And it, like DALI 3, it used the improved caption. The difference is it doesn't train the similar thing is it recaption and fix the caption. But the difference is that first, it doesn't use a customized captioner. It uses a state of art. We talk it a bit later, a bit before, that in a multimodal. So that is a COG VIM. This one is considered to be the state of art vision language model. But I'm a bit surprised that on the leaderboard I'm just showing you, it ranked pretty low among in the list. But what I heard before and I tried, I haven't actually used it on my local machine because it seems that it frequently consistently generates some errors when I run it on my local machine. So I don't know why it is. I haven't have enough time to solve these issues. But what people saying that this is one of the best vision language models, except that on the leaderboard I just show you, it is not rank that well. But Stable Diffusion 3 use this one as the captioner. So because this one is a large range model on the backbone, so I can imagine that there's very a lot of way to ask the model to generate different style of the text description. You can either ask it to generate long detailed description or ask it to generate a structure output, maybe a tag or something like the style, like a style common something, and like the color space, like the some certain description, the object, what is object in it. It's kind of like the mini GPD V2. It has a multi format. It actually I will introduce talk about later next week because they are very related to our subject. Okay, but anyway, this one is they use cog VMLM to generate to recapture the images. And another thing is that they only use 50-50 mixing ratio for the synthetic caption and the original caption. This is because the cog VM doesn't generate that well. So some vocabulary doesn't used for cog VMM when generating. So their experience shows that they still need, um, although the original captions are may not be that good, but it can still accompany with the high quality caption generated by CogVM, so that the model can be suited for a wider range of text prompt input. So here shows some improved text to image backbone. I mean that is one thing, and another improvement is the text architecture, or the very complicated and intimidating architecture we are talking about before. So it uses 3 different text encoder. So that's one improvement. In this case, it can actually generate quite good text output, like you can see in this banner, the monkey holds. It has generated very clear. This is a comparison of the training with all text encoder and without text encoder. It turns out that even without T5, it can generate quite good text information on the detail. But still, when the T5 is get into the architecture, it can still improve a lot of the qualities. So that's the improved text to image backbone is the backbone that the architecture we are talking about. And it used some data preprocessing, like filtering the NSFW images, low quality images, and also it pre-computing the image and the text embedding. Because you can see that the text embedding is a little bit more complicated than before. So it can make sense that we compute the the text embedding beforehand. So the embedding is pre-calculated, pre-computed, not that they computed online. So to speed up the things. And also because the image has to be petrified. Sorry, not petrified. Need to be encoded into latent space. So they pre-computed the latent of the images beforehand and train on the latent space, on the latent dataset. Also, they provide a lot of different optimization improvement like QK normalization, positional encoding, of, for variant aspect ratio, and the resolution dependent shifting, time schedules. Those are all details that when you wish to design the architecture or design the training process, those are all the details that you are worry about or consider about when, and need you to make some decision. So what kind of position encoding it is, 1D or 2D? So what about the spatial ratio is change? What about different resolutions? So do we have to change the time step schedule when the resolution is different? All of these kind of things and more. Not only this one, but I think we really appreciate this paper provide their insight and their result and their decision on all these topics, because these are the things that um, are very valuable. So and we can consider about it because we don't have that many computational power to do the comparison experiments. But compared to the previous topics, these things are considered a little bit minor. So I'm not going to cover it today. But if you are interested in the previous thing, I encourage you to read the Stable Diffusion paper. And it actually provides some insight and details consideration about these topics. So these are the images generated by Stable Diffusion and presented in the paper. It actually gave you public API to the Stable Diffusion 3. You have a free credit to generate the images by using Stable Diffusion. You can try it by yourself and to see how it works. And according to an announcement, it's promised that it will provide the training code and the weight also, if I remember correctly. So we are expecting to see this being released and waiting for them to be released in the near future. Okay, so that's all about today. We'll see you next week.